Did you know that polar bears like to walk? Polar bears can walk up to 20 miles or 30 kilometers per day for several days in a row, following seals, their favorite prey, across Arctic ice sheets. Let's use this in an example to illustrate the logic of hypothesis testing. So we do a literature review, and we find that the typical polar bear will walk about 100 kilometers in a week. Now, this 100-kilometer number is a round number, and we know that round numbers are always liars. So you are right to be skeptical, and yes, this number is realistic, but not an actual mean. But with that full disclosure, we're going to use this 100-kilometer per week parameter for purposes of this example. We are going to say that on the average, polar bears walk 100 kilometers per week, and this is the population mean. Mu equals 100. If I draw a sample from a population with a mean of 100, what do you predict that the sample mean will be? 100. If I draw a second sample from a population with a mean of 100, what do you predict that sample mean will be? Also 100. If I draw a third sample from a population with a mean of 100, what do you predict that sample mean will be? 100. The mean of the sample should be the same as the mean of the population from which it was drawn. Now, we're going to assign the first group to be our experimental group, and the next two groups to be control groups. Now, in a real experiment, we would have no need for two control groups, but I'm doing this for a reason, to illustrate changes due to chance and changes due to an effect. We do a treatment on sample 1, the experimental group. The treatment comes from another discovery that we made during our literature review, and that is that whales, given caffeine, swim 48% further than similar whales with no caffeine. Knowing that caffeine led to a 48% improvement in the whales, we scour the literature and find that this effect has not been studied in other Arctic creatures. A gap in the literature. Let's do an experiment. Our research question: will giving polar bears caffeine make them walk farther? After treatment, we measure each of our samples again. We want to know which sample means represent the population mean of 100 and why. Let's start with our control groups. The sample mean for control group 1 is 100. Does that sample mean represent the population mean? Yes, it is exactly the same as the population mean, so it represents the population mean quite well. In fact, we couldn't ask for better. The sample mean for control group 2 is 104. Does that sample mean represent the population mean? Well, it's not exactly the same as the population mean, but it's still pretty close. I think that the sample mean for control group 2 is really the same as the population mean of 100, and the 4-point difference is best explained by random chance, or measurement error. Now, the sample mean for the experimental group is 150. Does that sample mean represent the population mean? Now I'm beginning to have my doubts. I'm not so sure I can explain a 50-point difference just by random chance. I'm skeptical. So how do I explain this sample mean of 150 among the polar bears who consumed caffeine? Here are my options for explaining the traveling bears, or the traveling wilberries. First, the sample mean for the experimental group, 150, could still represent the population mean of 100, but with a lot of random error. 2, the sample mean for the experimental group, 150, could represent a different population mean. It could represent the population mean we would expect with 48% caffeine-improved performance. That population mean of 148, 48% of 100, with 2 points of random error. So which is more likely? Does the sample mean of 150 more likely represent the population from which it was drawn, or the population expected if caffeine improves performance by 48%. As I said, this is about hypothesis testing. So let's examine those hypotheses again. The null hypothesis states that sample 1 represents a population with a mean of 100. We would write that H sub 0 mu equals 100. The experimental or alternative hypothesis states that sample 1 does not represent a population with a mean of 100 and better represents a population with a mean of 148. We would write that alternative as H sub 1 colon mu does not equal 100. To answer our research question, we could calculate the probability that sample 1 represents each of the two populations, 100 and 148, and then go with the higher probability, the one that is more likely. We will find that it is more likely that sample 1 represents a population with a mean of 148. So ultimately, we will reject the null hypothesis that says that sample 1 represents a population with a mean of 100.